Welcome to today's FDTD Go 16 Applications webinar. Today we're pleased to have Christopher White from the Huntsville, Alabama WFO leading the presentation for today. He's going to talk about the Nighttime Microphysics RGB for detection of fog, low stratus, and nighttime boundary layer gradients. So before we begin, just a few logistics. These are all recorded, and if you'd like to find the recording of this afterwards, you can go to the Visit webpage and look for the Satellite Chat library for all past recordings. Also, if you're interested in leading one of these in the future, we're looking for speakers, so just let us know. We'll also ask at the end here along with our contacts. Just a few of the webinar protocols to follow. We'll have about 20 minutes for our speaker. You can send questions via the GoToChat if you'd like, but also at the end we'll have a Q&A once Chris is done talking. Up to 10 minutes, so we'll definitely be done by 17:30 UTC. Remember, do not press hold, and also mute your phone when you're not talking. So at this point, I will turn it over to Chris.
Okay, thanks, Dan. Let's see here. Okay, so let me put it in play mode. And can you see my screen?
Yeah, looks good.
Okay, all right, great. Okay, so I want to very quickly thank Dan and everyone at FDTD for the opportunity to do this today. And so I'm just going to go ahead and jump on in because I'm notoriously long-winded and I don't want to go for 37 minutes or so. So, all right, so let me start off. And what I am talking about today is the Nighttime Microphysics RGB. I do see some mentions of this RGB around the country here and there, and some AFDs and stuff, and also just talking with some forecasters. I know it's getting some use at some offices. During the proving ground, the sport group I worked with, we shared this imagery with a number of offices, and of course at that time it was just from the polar orbiters. So the Alaska offices have gotten a lot of use out of this one, and still do. But I know it's really new to a lot of people, as is just the concepts of RGBs in general. So I'm going to talk a little bit about that too, and some of the issues associated just with RGBs. So to get started, so the Nighttime Microphysics RGB, I just wanted to show everyone in the menu system where this is located. So under satellite, you go to 16, that's the way it's set up right now, and then you go down to the RGB composites. And in this example, I just chose the center conus domain. And then it's down near the bottom under the advanced section, that's the Nighttime Microphysics. And I'm just going to zoom in that center conus menu, the RGBs, and then you can see it. And again, there's simple RGBs up here and then the advanced. And of course, this is the Nighttime Microphysics RGB under the advanced sections. So I just wanted to mention essentially the formula that comprises the Nighttime Microphysics RGB, and talk just very briefly about the constituent color components and the channel or channel differences that comprise those. So starting off looking at the red, notice that this is the 12.3 minus 10.35 micron band difference, and this is also known as the split window difference. And if you actually went in the channel differences under the satellite menu, you would see this band difference located in there. So with respect to clouds, generally what this means is if you have a small amount of red color, this commonly equates to a translucent cloud. And if you had a large contribution, typically that means it's a thick or an opaque cloud. Okay? And if you're in a clear sky condition, then a small contribution generally equates to higher relative low-level moisture, and then a larger contribution would be a lower relative low-level moisture. Okay? So now going to the green, and this is just a common fog product. So this is the 10.35 minus 3.9 micron band difference. Small contributions, there could be a range of this, but commonly it's going to be equated with some sort of a cold cloud or ice particles within the cloud. And then a larger contribution, depending upon how large, it could be water clouds with large droplets, and you'll get some sort of maybe a medium green value in those, although there are caveats to that. And then some of the largest values are equated to water clouds with small water droplets. Okay. And so then the blue color contribution is simply the 1035 micron band, or in this is, of course, just the clean window. And small contributions of this, or low values of blue would equate to colder temperatures, whereas higher values of blue equate to warmer temperatures. Okay, so it's important to remember that the RGB is constructed in 3D color space with combinations from each one of those colors lending to the final pixel color. Okay, and just also to note that if you actually take 255, or actually 256, and multiply it, 3 times, you're going to get a number that's over 16 million, well over. Now, the human eye, we can't even discern that many colors, but it is possible and actually you can get that many colors when you take and combine, a 24-bit image. So there are a lot of possible colors, and of course, the RGBs, they're going to be an issue for people who suffer from color blindness or other other sort of color visual inabilities. So obviously, people are going to want to keep that in mind. Okay. So in this example here, and this was an image from this was from several years ago. So let's first kind of focus on part of the southeast here, and it's going to be an area where we have relatively high contributions of red, say here over parts of central Alabama and central Georgia. We also have relatively high contributions of green here, and at least in this scene, relatively high contributions of blue. And so the end result from that you get is kind of a grayish color when you have relatively equal mixes of all 3 colors. And notice that where you have the brightest of these contributions, the clouds appear, not quite white, but certainly a light gray here, say in central Georgia. Contrasting that, let's go and look over the cloud scene here over Missouri. So here we have a fair amount of red, maybe a moderate amount you might call it in this particular cloud scene. And then looking over the same area, generally we have a lack of green color, it's very dark, and also a lack of blue color here. And this, of course, the low blue would indicate very cold clouds, whereas the green here would indicate probably some sort of an ice cloud. And so then, in fact, when you look at this image, what you see then is mostly it's dominated by red here because most of the color contribution is simply from red in a lot of these areas here, say in northern and central Missouri and a good swath of central Illinois. And this is actually going to be indicative of our higher clouds, cirrus clouds, and sometimes these can be relatively thin. So with that in mind, it may not be a bad idea to kind of revisit color theory when looking at or kind of thinking about RGBs, especially initially until you get used to them. It could be a good idea to go pull up a standard color wheel. You can do this online. This is just an example actually from PowerPoint itself, where I just pulled up a kind of a random box and it had a default color in there. And as you can see, it's got a red, green, and a blue. All those color components go up to make actually the color of this box here. So believe it or not, it does have red in it, of course. And you can, of course, move these values around and see what sort of a color that results from that. And it may help reinforce some things about color theory. Noticing that when you have the highest contributions of all colors, that is actually white, and then of course the lack of all colors is black. And then depending upon the various amounts of red, green, and blue, well, you're somewhere in between those two. So let's look at an example. Individual color contributions may not always be as they seem. So here it was a cloud scene, and this was just from a couple of days ago over a good portion of the Ohio and Tennessee valleys and some adjacent areas. And what we're first going to pay attention to is this cloud feature here in West Tennessee. And I sampled over that. And notice that in this case, we have a red, and I'm going to kind of focus on the red color when looking at the issue I'm going to talk about here. So notice that the red color, the contribution from this is at 121, or 47% of the total possible value for red in this case. So when we would initially look up here in the Midwest, we might think, well, there's not as much, it doesn't look as red, so there's not as much red. But that's actually not the case. In fact, there's quite a bit more red. Here we go from 47% to 62%. So the thing is that you're actually getting a lot more green and blue contribution, so it doesn't look as red, because now it has these other colors, and again, within 3D color space, that determine what is the ultimate final color. And now let's look for, again, up here, let's say look around Chicago and the Great Lakes. And what we would think here is that, well, it doesn't look red, but actually, again, it even has more red. And then also here, we have greater contributions of green and blue. So I wanted to say that individual color contributions may not always be as they seem, and it's important when you're viewing the RGBs initially to turn your sampling on and pay very close attention to how these color contributions are changing, because it does have importance with the actual physical characteristics of the clouds at which you're observing, or maybe the clear sky conditions you're observing. Okay. So now let's get into a little bit of some examples here, and we'll show how the RGB differs from some of the legacy imagery with which you're probably familiar. So in this case, what I'm starting off looking at is just a simple fog product, but the fog product. And this is a 10.35 minus 3.9 band difference. And this is just a typical grayscale of the fog product. And as is typical, at least I think, with the type of color maps that are used for this product, low clouds, stratus, and fog are going to appear generally lighter shading, and then darker cirrus clouds are going to appear black. Okay, so immediately we can relatively easily pick out some fog areas. Notice here there's some in northern Illinois. There's some areas scattered around the southeast, and also here in parts of the upper Ohio Valley and the mid-Atlantic. But when we go to the RGB, this is how low clouds will appear. And I'm just going to toggle back and forth for a moment. And I do think it is relatively easier to identify the low clouds, the stratus, and the fog in the RGB. And a lot of this is really just due to color contrast, okay? Now, you might argue that, well, that you could probably do some sort of a color map with the 10.35 minus 3.9 to make these pop out a little more. And in fact, you can. But you're getting a more complete depiction of the atmosphere in this case, because we also have the contributions of other important channels and channel differences. So in this particular scene, yes, the fog and low stratus do appear these general lighter shades of cloud up here, also down here, and you can see them dotted across parts of the south, while the colder, deeper clouds are going to appear these reds and oranges that you see along some sort of an old boundary right across, cutting across anywhere from Oklahoma up into the northeast and mid-Atlantic. And then I'll point out some other interesting features about this image a little bit later. But we're mainly, for the purposes of this talk, going to focus largely on these low clouds, okay? And I want to point out one thing here too. Notice that the low clouds in the stratus here in northern Illinois appear rather different than the ones down here in the southeast. And I'll turn on some observations from that morning, and these are actually the aviation observations. And notice that they're fairly similar. Up here I have bases, it looks like around 1,600 feet, 2,000 feet. And at least I have one observation under this cloud deck here. It's a little lower, about 1,000 feet. But these clouds do appear rather different. So I wanted to discuss that and then make the point that clouds across different regimes will look a little bit differently, across different weather and climate regimes, okay? So let's focus on these two different areas right here. So, and this is again the cloud scene over northern Illinois and the cloud scene over eastern Mississippi. And initially, we notice that the red values are quite a bit higher here over northern Illinois than they are eastern Mississippi. So increased red generally equals increased cloud opacity. So these clouds might be just a little bit thicker here in northern Illinois than they are over eastern Mississippi, so that's something to take note of. Although, really, this isn't a drastic difference, especially when you get over cloud scenes, like over low stratus. So don't pay a whole lot of attention to the red. I think this may have a little more application, especially when it comes to the boundary layer moisture characteristics, which I'll talk about here in just a little bit. But anyway, so let's look at the green. The green is also quite a bit higher in this cloud scene over northern Illinois. Generally, we could equate larger amounts of green with a smaller water droplet size. So perhaps at least with some smaller water droplets than in this case here over the clouds in eastern Mississippi. And lastly, the blue. Notice that the blue is a little bit lower than the blue contribution here. So lower blue, lower temperatures, and that's what you might expect here if we're going from northern Illinois to eastern Mississippi, say. So temperatures there are a little bit cooler than they are here in eastern Mississippi. All right, so that's largely the reason for the differences in the appearance of these two actually very similar cloud types. Okay, another thing I wanted to point out, each color pixel is the result of specific combinations of red, green, and blue. So similar colors, as you see here, would indicate similar cloud conditions. Might indicate relatively similar cloud bases, cloud tops, and that kind of thing. So forecasters, they could use this information to determine characteristics of clouds, I think, a little more easily in the RGB across the cloud scene, like where observations do not exist. So if you're looking at Chicago and you have an observation here, you don't over other portions, say, of the southern tip of Lake Michigan, noting that these colors are all very similar, and then they thus will describe very similar characteristics physically, then you could generally assume that these cloud bases would probably be relatively homogeneous across this area. The same across this area right here in northern Illinois. And likewise in other places where you see similarities. In general, the clouds would have similar characteristics in those places, especially when you're looking within a very similar weather region or a climate region. So I just wanted to show an example, and I'm just going to loop through this rather slowly, because I know there may be a little bit of a delay. But so you can see the Nighttime Microphysics RGB in motion, and wanted to point out the movement of the low clouds. So it would probably be easy to determine with the movement of these up here, say in northern Illinois, that this is some sort of a low stratus deck. But notice how the clouds are very, they don't seem to be moving a lot here in eastern Ohio. So this is very likely some fog here. And the presence of some higher red contribution right here, and actually I think this was a little bit lower blue as well, even though fortunately I don't have this sampled right here, might also have indicated that there was slightly thinner clouds but higher clouds here. Sometimes you might be able to distinguish between fog and stratus decks within the Nighttime Microphysics RGB. I don't have a great example here, but with time and overlaying the RGB with some observations, you would begin to notice some of those in some cases. I've certainly seen some cases along the Gulf Coast. But anyway, so I just want to put this in motion and let you see the observation and how easy it is to pick out the low clouds, and even interspersed here as they are in some parts of the Carolinas. You can actually make out the low clouds pretty well here amongst some of the higher, deeper clouds that exist in the area. Now this is really an old school image, and this is back from the days of the polar orbiters, but I wanted to take a moment just to point this out, because the RGB recipe is largely the same as it was then using the polar orbiter imagery. But what we're looking at here, and this is with maybe a more familiar color map, this is the 11-39 imagery, and in this one, it's been coded such that low clouds and fog will appear as yellow colors, and then higher clouds appear as blue. So notice that it does appear as though there is some sort of fog and stratus over parts of the central Appalachians and down to the southern Appalachians. When I turn on the Nighttime Microphysics, it's really much easier to distinguish exactly where we do have some fog in these areas and then where we don't. And notice here that it's these light colors, these kind of grays and maybe light aqua colors that appear here over parts of the Appalachians. That's where we do, in fact, have the fog in the narrow valleys. And then a little bit later that morning, it looks like it's relatively widespread here in the 11-39, but when we look at the Nighttime Microphysics RGB, it's a little bit easier to note the fog really hugging the valleys. And also I wanted to point out the difference here in northwestern North Carolina. All you see is yellow here. When I have the Nighttime Microphysics on, actually the presence of the yellow color would indicate that this is a little bit of a higher based cloud. And so this was actually a mid-level cloud here. And you would have thought that this were fog or maybe some stratus, low stratus at the time, but it actually was not. So again, you're getting a more complete depiction of the atmosphere with the RGB. Here's another example, and this was actually just this is from late June. And I'm at 10.35 minus 3.9. And by the way, this is just a standard kind of a color curve that comes up in our AWIPS here at the Huntsville office for this channel difference. But anyway, notice that you get relatively similar colors in the 10.5-39 here in this cloud scene over northern Mississippi, and this very large area here in the Mid-Atlantic and the Central Appalachians and Southern Appalachians. Notice that you get fairly similar green values. When I go to the Nighttime Microphysics RGB, actually what I'm noting here is I'm looking at some low clouds and some mid clouds. And here, what I actually have is thin cirrus. So this is an issue with the 10.35-39, and is that relatively thin cirrus will sometimes give you similar values as it would some sort of a lower cloud feature. So again, why I think the Nighttime Microphysics RGB can be advantageous. Here's another cloud scene, actually from just a little bit earlier here in July. What these actually turn out to be here, this is, again, what we're looking at here is the 10.3-39, and this is just the grayscale, of course. But you might think that the lighter clouds would be indicative of fairly low clouds and or fog. Yet, actually, when I went to the RGB, this is actually a mid and a high cloud partly here. So again, it's easier to distinguish different cloud types from each other, especially when you get mid clouds to low clouds, as in this case. Okay, so another potential application of the imagery is for the identification of low-level moisture boundaries. And in this case, notice that I have relatively low amounts of red, and that's what we're going to focus on here. And I sampled here in northern Alabama. And then I sampled this area right here where you have this obvious lighter color shading here. And notice that my red value is quite a bit higher. So again, lower amounts of red generally equate to higher low-level moisture, and higher red indicates relatively low-level moisture. So what we're going to look and see is what happened to my cloud scene in this area, because it would indicate that maybe I had a little deeper moisture over parts of northern Alabama as say I did over here, maybe over parts of central Alabama. Okay. So now we're going to zoom in here, and I'm going to focus on this area. Okay. I've highlighted here as the area with deeper moisture. Now we'll step through time in the visible imagery, and notice that as I get into the morning time and I start mixing, I'm getting the low cloud development actually in that area generally where there seem to be deeper low-level moisture, especially as compared to adjacent areas where the red component would have suggested I had lower low-level moisture content. So this might be useful for forecasting purposes to determine areas where low clouds are more likely to develop initially, where I might get some sort of a convective initiation. And it will also be important to pay attention to those boundaries, too, between moisture. And in fact, here's a couple of radar images showing that indeed I did get the deepest and best convection over that area of northern Alabama that day. Although some, of course, did drift into the area with relatively low moisture. And then again, I want to go back and point out a previous image I had shown, and notice that here I have a general lesser amount of, red coloration, or actually this image down here appears much bluer, and this appears much more red, even though what has actually happened here, and I have to go back to remind myself what it's the lower red, yeah, so here we go. So it's lower red contributions here would indicate higher relative low-level moisture, and higher amounts here mean lower, so it's kind of flip-flopped. But basically, I could identify a boundary here, and there was a front, when it was actually a little bit hard to determine exactly where the drier air mass was moving into our area. And this was actually just a few days ago. So we could obviously see the drier air mass now moving into the Tennessee Valley, and we were still well within the maritime air mass. So a few learning tips. It's probably good to use RGBs, especially initially, with the other imagery with which you're familiar. So it's still probably good to look at this in concert with something like the 10.3-10 or 10.3-39 to help you gain familiarity with cloud features. It might also be a good idea to observe some of the other constituent bands that make up the RGB. And then when you're looking at those, notice how those temperature values are changing and what that really means for the RGB. It's also a good idea to access some reference materials through the Air Tool and AWIPS. And I don't know if many of you know about this feature in AWIPS. Some of you do, some of you may not. But if you were to right-click on the product at the bottom, you'll get up through a little window here, and you right-click and hold. And then what you're going to select is Reference on Product. And then there are some training materials that do appear in the virtual lab. And these also appear with all the individual bands, too. There are fact sheets with those that you can access, actually through AWIP. So I want to make sure everyone knew that. So the main takeaways here are that the Nighttime Microphysics RGB can be used to identify low cloud features such as fog and low stratus, and it offers better contrast and legacy imagery, at least in my opinion. The Nighttime Microphysics RGB can be used to help identify areas of contrasting low-level moisture. It's also important to use unfamiliar imagery, like the RGB that may be unfamiliar, along with what you do know. And lastly, if you don't like any of these applications, you could consider the Nighttime Microphysics RGB for wall art. It does make very nice modern art or abstract art. And this is actually a picture hanging in my girlfriend's living room wall. There's a long story with that. But anyway, just wanted to see if there are any questions out there. And I want to thank Dan, Vika, Scott Lindstrom, Brian Mata, and also Emily Barrett from Sport and Kevin Fuel from Sport as well. Thank you.
Okay, any questions for Chris? One last call. Any questions or comments or discussion points for Chris?
It was all so clear, right?
Hey, Dan.
Go ahead, Ed.
I actually typed in a question, but I guess, I don't know if you saw it. I was going to ask, you were talking about higher bases, but can we really say anything about the bases of the cloud?
In which case here?
I think you said that a few times, but are we really saying the clouds are thicker?
The bases will be relatively similar. At least that's been my experience. Because, of course, you're not sensing the cloud base, you're sensing the cloud top.
Right, yeah.
Yeah. So, but in general, if the clouds are a little bit thinner, you might get a little more bleeding through of Earth's background microwave radiation, for example. It just depends on the opacity of the cloud. But what you'll probably notice is that in cloud scenes with colors, like, for example, in this case here that I had shown up here in northern Illinois, they'll be similar within reason. Now, within reason, might you cross important aviation thresholds like MVFR to IFR? Certainly. And, of course, there are other interesting tools out there for that, and, of course, there's observations.
Right.
But yeah, generally, I mean, in stratus decks over relatively small areas, you're not getting an enormous difference in the cloud bases anyway. I would encourage you to go in there and look and see what you see with this RGB. But yeah, my experience has been that, in general, when I'm looking at a cloud feature like the one here in northern Illinois, the one down there in eastern Mississippi, where the colors are fairly similar, I have relatively homogeneous bases even in a lot of those cases.
Okay, thanks.
Yeah, well, that's a good question.
Any other questions for Chris? Okay, well, hearing none, I want to go ahead and thank Chris for taking the time to lead this discussion today. And we'll announce our next webinar here shortly. There will be one on August 1st next week at 17Z. Someone from NHC will be discussing current tropical cyclone activity. Thanks, everybody, for attending, and have a great day.